we're talking about permission operators, and as we've defined, a permission operator is when X equals to its own adjoint, right? So we've been talking about the completeness of its eigenspectrum, eigensystem. Its eigenvalues are always real, and that's very important because quantum mechanics tells us that the outcome of an experiment trying to measure the observable related to X can only take the eigenvalues of X. Right? So if we're talking about energy, it will be the Hamiltonian. If it's momentum, it will be the momentum operator. Spin will be the spin operator, and so on. So this is why, the physical reason why we care about permission operators, because it's core to what the range of observables are in any quantum mechanical system. Furthermore, because the spectrum is complete, we use the eigenstates of the observable to try to describe the system, the possible physical states of the system, because it spans the eigenvectors themselves span the very vector space that our system lives in, right? And so that also brings us to the idea of compatibility, right? And so in any quantum system, we ask the question, what is the maximal set of compatible observables? Which means, what's the maximal number? What are the maximal set of permission operators that commute with one another, which mutually commute with one another? And that would give us the range of eigenvalues and eigenstates that we can use to label our quantum system. Okay, and so in fact today I'm going to tell you what happens if they don't commute. And this is the famous uncertainty principle, right? So if they don't commute, then you cannot you cannot simultaneously diagonalize then X and Y cannot be simultaneously diagonalized. You cannot, and so you cannot determine the respective observables through infinite precision simultaneously. So let's see what that actually means. Okay. The first one becomes nice squeaky. So this is the uncertainty principle. If you may have seen when you were an undergrad, but usually it's often stated in terms of the position and the momentum eigenvalues. But what we want to see today is that the statement is much more general. Okay, it's more general in the sense that anytime a pair of observables do not commute, they will obey the same uncertainty principle. Yeah. So what's going to happen is first we're going to define the following object. So first we're going to define, so we're going to assume that x and y do not commute. Okay, and what we're going to do is going to call delta x the following. We're going to take x, the Hermitian observable itself, and then we're going to subtract it with respect to the expectation value of x with respect to some state that we care about. Okay, so this is called an expectation value. It just means you're taking the same cat and the same bra with respect to the same state. For the cat and the bra, taking the same state. Okay, and delta y is similarly going to be y minus, so kind of deviation from the mean. Roughly, right? That's why I put it in quotations, because these are operators, so we have to first understand what do we mean. Now, what we are going to see is that what we're going to see is that we're going to use the Cauchy-Schwarz inequality, and so let's remind ourselves what is the Cauchy-Schwarz. So Cauchy-Schwarz tells us that alpha alpha beta beta is greater or equals to alpha beta absolute value squared. Okay, and what we're going to calculate today is we're going to calculate the expectation value of delta x squared times the expectation value of delta y squared. Okay. And this you can think of as psi delta x psi. Okay, and then psi delta y psi. So split it up like that to show you that there's an exact parallel between the left-hand side of the Cauchy-Schwarz inequality with what we are writing down here. So this is basically alpha. Remember that this is Hermitian. So both delta x and delta y are Hermitian. Okay, because well, x and y are Hermitian, and the expectation value is just a real number. Okay, so why is it a real number? You can take the complex conjugate, and this is supposed to give you swap the bra and the cat, but it's the same thing. but it is supposed to take the dagger of x. But x is Hermitian, so therefore this is just equals to x. Which means that this expectation value is equals to its own complex conjugate. And when a complex number is equal to its own complex conjugate, it means it's real, right? So that is why this is Hermitian. Okay, the deviation from the mean is a Hermitian operator. It's a Hermitian operator minus a real number, essentially. Okay, and so if you like, we can write an identity. We can write an identity operator here and here, but I'm not going to do that. That's too much writing. So back to this guy, because it's Hermitian, this you can identify as alpha, bra, and this you can identify as alpha cat. And likewise, this guy you can identify as beta bra, and this is beta cat. And so immediately you can write down that this must be greater or equals to alpha beta inner product. Okay? So alpha is, remember, psi delta x, and then beta is delta y psi, and then the whole thing squared. Okay, so left-hand side, the delta x and delta y are factorized, but because of Cauchy-Schwarz, we're able to relate that to the product of these guys. Okay, and the square of the product of these guys, expectation value. So what we're going to do is we're going to do a bit of massaging of this right-hand side, and then we're going to see how to relate it to the commutator. Okay, that's the goal here. So the way to do it is to first recognize that when you have the product of any operator, actually let me just write it down for any operator. If you have the product of A and B, and these are operators, you can always write them as the average. Maybe I shouldn't. The average of AB plus BA, and then you add AB minus BA. Okay, this looks a little silly at first. Well, this will just cancel this because of the minus sign, and then AB with a half will give you back AB. It looks a little silly, but it's not silly if these guys are Hermitian. Right? So if A and B are Hermitian, then in fact, I believe it's your homework that you prove that AB dagger will be B dagger, A dagger. And what will happen is that if they are Hermitian, then you get BA. Right? So AB dagger is BA. So let's see what happens for these two groups of operators if I group them like that. So firstly, when you write it this way, there's a name for this. It's called the anti-commutator, okay, which I usually write it as a curly bracket. Sometimes you see people write it as a bracket with a plus below. And this one is a bracket with the minus, but I just call it a bracket, so I won't change my notation. Right? So this is the commutator, as we are familiar with now. And this is the anti-commutator. And so what we can see is that if you take the dagger of this guy, what happens? The dagger of this guy is, of course, then the dagger of the anti-commutator and of the commutator. Okay. In fact, there's a homework. I forgot what there's a homework now, but I think you will prove in your homework that let's do it for this guy first. Okay, so I think that one is your homework problem, if I'm not mistaken. So A, B anti-commutator is what is in fact, we already know it's AB plus BA, but we also know that AB dagger is just BA if they are permission, plus this guy becomes AB. But this guy is this guy, and this guy is this guy. So in fact, that means we get back the anti-commutator. Okay. So if, again, assuming that they are permission, right? But when we come to the anti-commutator, you will find that, in fact, even though even if A and B are permission, you don't get back itself. In fact, you will find that you get back negative of itself. Okay. So in other words, this is permission. But this guy is actually anti-permission. Anti-permission just means when you take the adjoint, you get back negative of yourself. Okay. But remember, this whole thing, AB, is actually going to be our delta x delta y, occurs inside an expectation value. Okay. So we should think about what that means. So remember, it's taking place inside an expectation value like that. Okay, so we have AB psi, and what we've done is we have broken it up into psi 1/2 anti-commutator plus 1/2 commutator. And this guy is permission. Okay, this is permission. Whereas this guy is anti-permission. And the issue here is that I want to illustrate is that this is a real number. And actually we proved it already. We showed that if you have a permission operator, its expectation value is a real number. Okay? So I won't do it again because we already showed that this is permission. Doesn't matter what form it takes. Right. Here is an anti-commutator, there is just an x. But the point is that if you take the expectation value, it's a real number. But if you have an anti-permission operator, it will turn out that this guy will be imaginary, purely imaginary. Right? So if z dagger equals to minus z, then let's take the complex conjugate of this object. And this is going to give you psi, and then z dagger psi. But if it's anti-permission, you get minus psi z psi. Which means that this complex number is equal to the negative of itself when you take the complex conjugate. That means it's purely imaginary. Okay, so this guy is purely imaginary. Okay. And so you have real, this thing is real, and this thing is purely imaginary. So we also remember on the right hand side we're taking the square of AB expectation value. Right? So the square of it must therefore just be the sum of the square of these guys. So it's 1/4 the square of sine AB plus 1/4 the square of the commutator. So let's see what we have here. Squeaky. Now let's plug in. Our A equals to delta X and B equals to delta Y. But before that, let me just do one more calculation. So that for us, A is X minus expectation value of X, and B is Y minus expectation value of Y. So these are just real numbers, okay? But when you calculate the commutator, what you have is X minus expectation value of X, Y minus expectation value of Y. So in your homework, you discover that the commutator is basically linear in both arguments. So you can distribute these guys out. So for example, you get X, Y, and then you get minus X expectation with Y, X operator commuted with expectation value of Y, and then of course you get plus expectation value of X, expectation value of Y. But these are all numbers. These guys are all numbers. So they automatically all commute, right? So this is 0, that's 0, that's 0, because all these are numbers. The expectation value is number. So the commutator of delta X and delta Y is just the commutator of X and Y. And so that's now our uncertainty relation. Okay, so sine of delta X squared sine of delta Y squared is greater or equals to the sum of these two guys. But these two guys are both squares. Okay, so they have something square for something square. So certainly, if this is greater or equal to the sum of these two squares, it must therefore be greater or equal to the one of the squares, right? Because this is always positive. So if this thing is always greater than the sum of them, it must be greater than the individual terms. And because we've calculated the commutator AB, we found that it's just equal to the commutator of x and y. Right, so it is purely imaginary, this number. So I'm going to take an absolute value, but it's purely imaginary. And that is, in fact, the famous uncertainty principle. Okay, so this is the famous uncertainty principle. So in some sense, you can think of this as the variance, right? The product of variances. Because it's the square of the deviation from the mean, right? And so that in turn, is telling you that the product of the variances cannot be zero. Why? Because it's greater or equals to the expectation, the square of the expectation value of the commutator. And because these observables we're assuming are not compatible, which means they don't commute, and therefore, because they don't commute, there's only so small the variance can be. Okay, the variance cannot be smaller than the product of the variances cannot be smaller than this quantity over here. Right? So this is basically why it's called uncertainty. Right? So for example, I'm sure you've seen this in quantum mechanics. So for example, in one dimension, you're probably used to the fact that the position operator, so this is now the position operator, commuted with the momentum operator is I times h bar. Okay, but so I'll tell you guys in a second. I'm going to set all my h bars to 1, and xp is, if it's equals to I, that means that psi of delta x squared times psi of delta p squared, in fact, is greater or equals to 1/4. This is I, so it's just basically greater than 1/4. There's an h bar here if you want, h bar squared over 4. So that is in fact something hopefully you guys have seen before. Delta x squared times delta p squared is greater or equals to h bar over 4. Right. You guys have seen this? Yes?
The delta x delta y is greater than h bar over sorry, delta p. Square root of it.
Yeah, sometimes you take the square root, yeah. But you may not have seen the top line before, right? So the whole point of doing this in a more abstract way is to show you the generality of the principles behind quantum mechanics, right? In some sense, it's just linear algebra, but because it's a bunch of operators, this is the more general statement. Any questions for me? No? Okay. Yeah, so maybe I should say a short blurb about h bars. So far I have not had a chance to write down h bar too many times because we're doing So about 2 months from now, you'll discover that this guy shows up in quantum mechanics as well. So you might think we're doing just classical mechanics. Right? How does it show up? It turns out that there is a different formulation of quantum mechanics from the one that we're doing now, which is called the path integration. So if you try to calculate the amplitude of going from some initial position to some final position, and later on we will learn that this amplitude is evolved through time using the Hamiltonian, something called the time evolution operator, which we'll talk on. So this turns out to be, roughly speaking, you start at time equals to 0, and then your initial position xi, and then you want to end up at time t at the position xf. It turns out that quantum mechanically, the way to calculate this is to in fact sum over all the possible paths. That go between xi to xf. And what shows up here is I times this action, whatever the kinetic energy of this particle is, whatever potential energy it has, and then you sum it over the exponential of this action, but you have to divide by h bar. Okay, so h bar will turn out to measure how quantum S is. Okay. If S over h bar is much, much bigger than 1, then usually this is classical, or at least semi-classical. Okay. If S over h bar is of order 1, or even less than 1, then this is a highly quantum process. Okay, that's one way to think about it. So I'll say this again when we get around to the path integral. But I just want to give you guys a flavor that it's not a completely sloppy thing. If you know, usually what happens is if you know what you're calculating, then even though you set your h bar to 1, you can recover it fairly easily by knowing what the dimension is of the object you're computing. Okay, so for example, very simple example. Okay, so when I know, so remember that h bar equals to 1, but because h bar originally is energy times time, so when you say that h bar is 1, that means that energy is now basically inverse time. Okay, and so how do you see a simple example? Well, you know that the energy of the photon is given by h bar times the angular frequency. So if h bar is 1, then energy equals to the angular frequency of the photon. But angular frequency, you know, is basically inverse time, right? So if you want to put back your h bar, suppose I didn't tell you this, and I just told you this is energy. Then I know that h bar itself is energy times time, so I know that I can just put back the h bar because I know the ultimate dimension of what I'm trying to calculate is of units energy. So that's a simple example. But once you know that, once you understand that, then you understand what needs to be done to put back the h bar. On the other hand, you can do it the other way around. If you put h bar to 1, you find that a lot of the dimensional analysis becomes easier because your dimensions, your base unit you're basically using H bar as the base unit for your angular momentum. And very often that ends up simplifying your dimensional analysis, because once you set that to 1, then energy equals to inverse time, and so you lose one dimension that you need to worry about, because energy is time. So both are interchangeable. Okay, so there's an advantage to that. But as we go along, hopefully we'll have more examples. Okay. Any questions for me about H bar equals to 1? I think the condensed matter physicists don't do that as often, but certainly in high energy physics and cosmology, it's something done very, very often. I don't know why the condensed matter people don't do it so often. When you read their books, they still put in all the H bars and all the C's and the Boltzmann constant and so on. Okay. So we should talk a little bit about the Born rule before we move on to unitary operators. So the Born rule, now that we have seen permission operators, can be stated more explicitly. Right? So if you have X as your permission operator, and you want to make, you have a quantum state, and you want to make a measurement. Then this is where the fact that you have a complete set of states comes in a very crucial way. So psi itself, you know, can be decomposed into the eigenstates of X. Okay, so X lambda is lambda, lambda. So these are the eigenstates of X. And as I've said before, its eigenstates are complete in the sense they span the space. So any quantum state can be decomposed into this basis. So what happens is that when you measure, when you set up an experiment and try to measure this observable, what are the outcomes? Well, the probability, the Born rule says that the probability that your psi will give you an outcome of, say, lambda naught, is simply given by whatever state you had, and you take the inner product with this particular state, squared. Right? So this amplitude is basically the coefficient of this particular state when you make this decomposition. And what the Born rules also say is that after you make the measurement, immediately after that, your state will be in lambda naught. Right? So immediately after, let me write it down. So that's a general statement about Born rule, right? If you have an observable, then your wave function collapses. That's how you would say it in the Copenhagen interpretation, right? And the probability of getting that particular outcome, lambda naught, the particular eigenvalue of the spectrum of X, is given by the amplitude, the overlap between the state and the eigenstate squared. And so, related to this is that if you make repeated measurements, then you can ask the question, what's the average outcome, right? So if you make many measurements, if you prepare the same state, and make many, let's say n with the infinity measurements, what's the average that you get? And this is actually what the interpretation of the expectation value is. Okay, so the answer is that the average is the expectation value. Why? Because let's do it. So if I insert a complete set of states, this is the completeness relation, and then I do another completeness relation over here. Okay. But because these are the eigenstates of X, right? So X applied to lambda is just lambda, lambda. And lambda prime acting on lambda, these are orthogonal. We can assume these are orthonormal states, right? And so therefore, the two sums will collapse to 1. And I'll just get lambda, psi, lambda. And remember that this is just lambda prime, lambda gives you a delta function, and you just get lambda, lambda, psi. Psi, lambda, lambda, psi is just a square. Of getting this state, the amplitude of getting this state. But what is that? This is basically saying that this is the outcome, that's the outcome times the probability that psi will be found in this state. Right? And probability times the outcome summed over all the possible outcomes. That's basically what we mean by the average. Right? So it's a quantum average. But you have to do this experiment basically infinite number of times before you will get this average. Right? But that's the intuitive sense of what it means, at least. Okay. All right. Any questions for me?
So the first grade is then the phi x phi is the definition value.
The Born rule is that is this side. The Born, you're asking about the Born rule, right? So the Born rule is that when you make a measurement, you will collapse the wave function to the eigenstate that corresponds to the outcome that you measured, right? So we already said that the possible outcomes that you can get when you are measuring X are the eigenstates, right? You cannot find your state to be anything else. When you make a measurement, if there's energy, then these will be the energy eigenstates. If it's momentum, it will be momentum eigenstate. So energy, if you make a measurement of energy, it will turn out to be an eigen energy of the Hamiltonian, and your wave function, your state, will be collapsed to the particular eigenstate corresponding to the energy that you found. So that's the Born rule. And the probability of that happening is the square of the amplitude. Right. That's the Born rule. The expectation value is just the interpretation. It's just the interpretation that this is the average value of your measurement. If you make the same measurement on exactly the same state over and over again for basically infinite number of times, then the average will turn out to be given by the expectation value. Yeah. Okay.